Welcome back to an introduction to programmable logic controllers, part 2. This is presented by the www.plcprofessor.com website and PLC Professor YouTube channel. This is an example of a relay control panel. Notice how everything is mounted in rows. The top row contains Allen Bradley relays, about 25 of them. The second row also contains about 25 relays, but the third row is made up of motor starters. Remember, I explained in an earlier presentation that motor starters are really 3-pole single throw relays or contact relays with the addition of something called motor overloads. These are thermally sensitive devices that will open the path for current flow if there is too much current. The key element to grasp from this photo is that there are many relays mounted in many rows. This is a graphic illustration of an industrial control panel. If we remove the face of the enclosure to reveal the actual backplate or panel, we see an array of brown rectangles that we are representing as individual relays. An actual panel would have additional devices, but our panel is made up of very neat rows of just relays, but they are not all identical. Looking at the relay control panel from a logical view, and simplifying the illustration by showing all of the input devices with their cables landing on terminal strips on the left end of the panel, and all of the output devices with their cables landing on the right side of the panel, and each to separate terminal strips. So you see 2 rows of yellow relays, and then on one end you see a row of terminal strips, and then on the other end of the panel. So ordinarily input and output devices would not be separated out like this. But for the sake of our illustration and explaining how a relay control panel functions, this is necessary. Now, all the relays on this panel are probably of this type. In the previous slide, all the relays were brown, but now we have a column of yellow relays on each end. These are the interface between the input and output field devices. The input devices are proximity switches to detect the presence of objects in close proximity. They're non-contact. They function by emanating a field, either magnetic or electrostatic, from the face of the device, and then changing state when the field is disturbed by the presence of an object. I demonstrated this to some degree in a previous lecture on basic electricity and magnetism. And then also for input devices we have photoelectric switches or photo eyes. These are another presence sensing type of device that function by changing state, going from off to on to off. When a beam of light is broken, if it's a through beam type photo eye, or the device senses reflected light. You have 2 types of photo eyes. There are those that are called through beam. In other words, you have a sensor on one side of a path of travel, and then you have a light source on the other. And when the object goes by and breaks the beam, the sensor says, aha, something's passing by. You have other devices that, for instance, the one right in front there, you can see it has 2 lenses. Looks like 2 eyes. One of those emits light, and the other looks for light reflected back. So when an object passes by and the special frequency of light is reflected off of that object back into the other lens, it detects the presence. Besides proximity switches and photo eyes, we also have limit switches, and they're one of the oldest presence sensing devices, sensing presence by actual contact with an actuator on top of the device that operates a switch. 2 of those you can see a plunger with a little wheel. The other 2 would require an additional item that you purchase called an actuating arm that's adjustable both in length and angle. Also, condition switches, which have been around quite some time, they operate a switch when a temperature or pressure change is sensed. All of these devices are digital. That is to say, they have two states. They're either on or off. The bulk of the relays are the internal relay logic that respond to the changes in the state of input devices or respond to a combination of states of several input devices. Output devices are most often motor starters. We saw a few motor starters in the previous slide. These are devices that control electric motors. What you see in front of you are all 3-pole devices for 3-phase, which is a special format of electricity that gives you much smoother and much greater power than single phase. So these are 3-pole relays. You know, when you actuate them or energize them, they switch 3 poles or 3 separate paths of conduction in and out. The only access to the state of logic on this type of panel are through illuminated indicators. So on a regular relay panel where you don't have a computer screen, you have indicators. So these indicators are wired in as outputs. When certain conditions are met, a light will turn on the front of the panel to indicate that the conditions have been met and you're in a certain step or phase of the process. And most processes these days have solenoid valves. There's more than just solenoid valves, so we say solenoids, but 90% of the time there's solenoid valves. In an earlier presentation, we talked about these solenoid valves and their functionality with cylinders. All of the products that you see on the screen here are available from Allen Bradley, which manufactures industrial control products. There are other companies that make similar products. This particular company, Allen Bradley, has probably the largest array. The only item that they do not sell, manufacture and sell, are the solenoid valves. Although a real relay panel would not be arranged this neatly, the idea is the same. There are relays that are energized by means of input devices. There are relays that are strictly internal to the logical machinations of the process. We call that relay logic. In other words, they don't actually directly respond to an input device, but they might respond to a group of input devices, so they're logical relays. And then, of course, we have relays that switch the output devices on and off as programmed. For the sake of illustration, we have enlarged the panel and increased the number of rows to 16 rows of relays. Next, we will rotate the panel to conveniently give us rows of 16 relays, and we will pretend that we have 8,000 rows of 16 relays. Actually, in computer land, 1K is not really 1,000 and 8K is not really 8,000. And you will see why later when we talk about the binary number system. For now, however, we are pretending that we have 8,192 rows of 16 really small relays. So we now are going to identify our relays by row and position. That is to say that we have coils 0 through 15 in row 0, and we have 0 through 8,191 rows, which is a total of 8,192. Because in computer land, everything starts with 0. If this were relay coils, it would be, we would have row 1 through row 8,192, and we would have coil 1 through 16. If you look at one coil here, and we'll take the last coil in the first row. So we would identify this coil as row 0, coil 15. If we look at it, we'll see that it's a coil with one form C contact. Now we know that that relay coil and contacts could be a number of other configurations, but remember, we're making a transition now to bits in memory. If we need more contacts for that coil, we just simply add more contact blocks. Now that was an awful lot of information to take in a short time. So give yourself a break, get up and take a stretch, get something to drink, and come on back. There are several number systems made use of in the human interface to programmable logic controllers. At the fundamental level, at the actual computer electronic level, everything in any computer is binary. Binary is a base 2 number system. 2 states, 0 and 1, digital, on or off, yes or no, true or false. Everything is absolutely binary. There's nothing but ones or zeros in any digital computer system. Therefore, decimal, hexadecimal, octal, and binary coded decimal are used to interpret the binary values present in the memory of the programmable logic controller and display them on the screen in the programming software. Whereas they are always binary in the PLC, on our graphical user interface like RS Logix 500, RS Logix 5000, or any programming software, we may see a decimal value, we may see a hexadecimal value, but they are representing binary numbers. The binary number system is second nature to us, so we will use it as a springboard into binary. To do that, first we're going to look at the decimal system as we see it. You have indexing, positional notation, exponential. Indexing would be like an odometer. So if you look at the highlighted area there, and you see 0 through 9 in various vertical positions. So if you take the least significant digit, which would be the 0 to the far right, for every 10 clicks of that position, the next position to the left is going to click once. So the second position from the least, the second least significant digit, is a 10 counter. The third position is going to click once for every 10 clicks of the second position, which clicks once for every 10 clicks of the first position. So that's 1 times 10 times 10, so that's 370. So the third position is a multiple of 100, and of course, decimal's all second nature to us. So indexing like an odometer. In exponential, we have units, and then we have 10 to the first power, 10 to the second power, 10 cubed, 10 to the fourth, 10 to the fifth, and 10 to the sixth. In positional notation, which really is the one that we're the most familiar with, is ones, tens, hundreds, thousands, 10,000s, 100,000s, and millions. Again, if you start with the units position, which is the least significant digit all the way to the right, ones, you simply multiply by 10, by 10, by 10, by 10, by 10, by 10 to get to a million. Okay, everybody understands this. This is second nature to us. If I were to rip off a number and say 5,785,934, you can picture that number in your mind. You could write it down. You could repeat it. And if I said dollars, you would instantly have a relatively good idea of what that was worth, the actual value. Here we have, again, three representations of the same value. 40,000. 4 times 10 times 10 times 10. 4 times 10 to the fourth. So again, everyone observing this understands the decimal number system and is very, very intimate and familiar with it. Binary, on the other hand, now we're showing this exactly the way we did decimal. So there's there's decimal, indexing, exponential, positional notation, and here's binary. Decimal, binary. Indexing, whereas in decimal it took 10 clicks to get the next significant digit to click once. With binary, 2 clicks and the next one clicks once. Exponential, units times 2 times 2 times 2 times 2 times 2 times 2, or 10 to the first, 10 squared. I'm sorry. I'm so used to saying scientific notation. 10 to the 0 power is units. 10 to the first power is twos. 2 to the second power is fours. 2 to the third power is eights, and so on. Now here's an interesting point. Notice that the exponent on the base 2 number system goes beyond 2 characters. So in the binary number system, there's only 2 characters, 0 and 1. There is not a 2. 2 is not part of the binary number system. It's zeros and ones. So if you get 2 clicks on the least significant digit, then the next position goes to 1. Well, there isn't really a name for any of these positions, just like over in positional notation. We typically say 1, 2, 4, 8, 6, 1, 2, 4, 8, 16, 32, 64, times 2 is 128, times 2 is 256, 512, 1024, 2048, 4096, 8192, 16384, and so on. But in order to describe anything between human beings and the binary number system, other than saying 1 or 0, we have to use the decimal or base 10 number system. Otherwise, nobody would have a clue what we were talking about. So keep this in mind. There are no words in the English language to describe anything in the binary number system other than 0 and 1. We say we have a 2. We say we have a 4. We say we have an 8. But 2, 4, and 8 are not words that describe the binary number system. So the binary number system is in a land all by itself. There is no way to talk it. No one can talk binary. Okay, hexadecimal, base 16 number system. We're not going to elaborate as much on this. However, and you haven't really looked at it yet, if you take a 16-bit binary word, that's 16 positions, and in each position you have a 0 or a 1. For hexadecimal, you can break up those 16 positions into 4 groups of 4 bits. And then each group of 4 bits is represented as you see here in this diagram. So 4 zeros is 0, and if you go down through the first column there, you get to the bottom, you have an 8, no 4s, no 2s, no 1. Well, 8 and 1 is 9. However, the next position, 1 0 1 0 at the top of the column on the right hand side, that would be equivalent to decimal 10, but you can't use 10 as a single symbol to represent one value. So in other words, for the first 10 positions, 0 through 9, or 4 zeros through 1 0 1, we could use a single character, 0 through 9, to represent the value. But when we get to the top of the next column, we can't put in 1 0 as a single symbol. So instead we use A, B, C, D, E, and F to complete these 16 possibilities for 4 binary digits. In other words, if you take 0 0 0 0, which equals 0, if you take all the possible combinations of those 4 bits, you see them all right here. So For 3 bits, there are 8 combinations. For 4 bits, there are 16 combinations. For 5, there would be 32, and so on. For each additional binary position, you double the total number of combinations. So if we look at the value over on the right there, 1011, in hexadecimal, 1011 is 11. So if you add up the binary values, look right above it, you see the blue arrows point down, and then you see 2 to the 0, 2 to the first, 2 squared, and 2 cubed, right? Well, you figure that out. You've got a 1, a 2, and then 2 cubed is 8. So 8 and 2 is 10, plus 1 is 11. You look over at 1011 in the white area there, equals B, 11. So B represents a hexadecimal 11. We don't use a lot of hexadecimal in programmable logic controllers anymore, but you will see it, especially when it comes to something called a mask. There are certain instructions that use mask, and they are usually represented in hexadecimal. So once again, our 1011, 8 plus 0 plus 2 plus 1 equals 11, hexadecimal. Now this is also hexadecimal. The previous one, 1011, when you look at that, you really don't know whether that's binary or decimal or hexadecimal. It's 1011. It could be 1011, or it could be hexadecimal 11. So typically you're going to see a subscript to the right and lower for the value. In this case, it would have an H. It would show that it was hexadecimal. Now, when you see a value like this one, A0F1, because you see alpha characters in there, you know it's hexadecimal. This value right here is really outside the scope of this lecture, but it shows you how difficult it is to deal with any number system other than decimal. I mean, binary is not real bad, but hexadecimal and octal become very difficult. Okay, binary coded decimal is another variation, and you see they've divided up the 16 bits into 4 groups of 4 bits. The difference is, in BCD, the equivalent decimal value of any group of 4 bits will never exceed 9, because this is binary coded decimal. The conversion value has to be decimal. So look at the top 16-bit word, 1000011010010010101. Well, you know, I just repeated that, read it off the screen, and I can't remember what I said. But if we go through and convert and add up a 1, a 4, a 16, 128, add 512, add 1024, and add 32,768, that adds up to 34,453 as a decimal equivalent. So you see the top 16 bits have a little 2 subscript equals 34,453 with a 10 next to it. That way you know it's decimal. Now we take those exact same 16 bits, drop them down, divide them up into groups of 4 bits, and we say the first 4 bits to the right are the ones, or the units. The next 4 are tens, the next 4 are hundreds, and the last 4 are thousands. So we have 8,000, then you have a 4 and a 2, that's 600. You have an 8 and a 1, that's 9, and you have a 4 and a 1, that's 5. But you don't add them all up. Those are the positions. 8695, 8,695. BCD, you see that a little more often in some of the older PLCs. In newer PLCs, there are instructions for BCD, to BCD and from BCD conversion instructions, but you're not going to see that much of either hex or BCD. Okay, octal, base 8 number system. Remember, we're talking about the number of symbols. Binary has 2 symbols, 0 and 1. Base 8 has 8 symbols, 0 through 7. Base 10, decimal, what we all know and love, has 10 symbols, 0 through 9. Hexadecimal has 16 symbols, 0 through 9, A, B, C, D, E, and F. So if we look at these bits here, 101000101, little subscript base 8, that's equivalent to 2,129,985 in base 10. The next value there, that's also base 8. That's the highest value you could have for base 8 for 8 positions. Because remember, the characters are 0 through 7. So 7777, 7777, you can't go any higher than that. That's it. 7 is the highest value in octal. You won't see this in any new PLC, but in the older PLC 5s, PLC 2s, especially the 1771 I/O configuration for what was called a rack of memory. You had a 2-slot addressing, 1-slot addressing, half-slot addressing, and it all revolved around the base 8 number system. I'm sure you have lots of questions, but this will basically take care of an introduction to different number systems. The one that we really care about the most is binary. Okay, binary digits, B-I-T-S, bits. That's where that term comes from. A bit is one position in a binary value. A nibble is 4, 8 bits is a byte, 16 bits is a word, 32 bits is either a double integer or a long word, and so forth. Now let's jump back to our enlarged array of relay coils and magically convert our array of relays into an array of individual microcircuits, each of which can individually be controlled into 2 states, on or off, just like a relay coil that can only be one of 2 states, on or off. So are the bits in memory. They are in one of 2 states, on or off. In binary, the closest that we can come to 1000 as positional notation is 1024. In other words, multiples of 10, 1, 10, 100, 1000. But with binary, it's 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 2 times that is 1024. For years now, the makers of computer memory have quantified their product in Ks of memory, or multiples of 1024. In recent years, the industry has strayed from this convention because the extra 24 elements really begin to add up when you get into mega and giga elements. So let's pick up one relay equivalent bit and examine its actual construction. You see that each bit is an actual microcircuit that is connected to the entire array of bits in such a way that it can be turned on or off, and in such a way that it can be read, or to say that it can be examined to determine which of the 2 states that it is in, on or off. So with relays, you use the normally open, normally closed context to query the coil as to its state. In computer memory, you read or write. You write to the bit to set it 1 or 0, and you read from it to see what its state is. Let's select another bit in the array. In the upper left-hand corner, you could say that these 2 bits are as far apart as possible in the memory array. What is the only difference between these 2 bits? Just think about that for a second. The address, or more correctly, the memory location. As we go along, you will notice more use of the term memory location than memory address. Before there were street names and house numbers, the word address was strictly a verb, never a noun. When we get into programming, we use the instructions that address memory locations, much as you address a person with a question or a statement, a read or write. When you make a statement addressing an individual, you're setting their state. If you ask a question, you're reading or determining their state. This fine point will make it easier to follow the description of logic programming. Okay, here's one last look at a relay. Let's take a tighter look at the symbols and functions. In a relay control system, the contacts are used in other circuits to indicate whether or not the mother coil is energized. So you could say that the normally closed contact has continuity if the relay coil is the normally closed contact of a relay has continuity if the coil of that relay is correct, de-energized. The relay de-energized is the normal state, so the normally closed contact will be normally closed when the coil is in its normal state of de-energized. True and false are an alternative to on and off. The normally closed contact is true if the relay is de-energized or off. The normally open contact is true if the relay coil is energized. Or you could say the normally open contact is true if the coil is energized. The normally closed contact is true if the coil is de-energized. After all, we are going to be talking about the state of bits of memory from here on, and they are on or off. Okay, we've replaced the relay now with a bit of memory. The symbol for the bit looks kind of like a circle, like a relay coil. Now, the reason that it has the shape it has, believe it or not, was in the early days a printer could not print a circle. So when you were printing out your PLC program, the closest they could come was an open and closed parentheses. And that's how we kind of got stuck with this symbol for the bit. And then, of course, you have what looks like a normally closed and normally open. How would you phrase? Now remember, these are instructions now, not contacts. But we're using the symbols from relay contacts to represent the instructions. So the first instruction over there on the left, it looks like a normally closed contact. This instruction is true if the bit is de-energized or energized. Correct, de-energized or off. This instruction is true if the bit in memory is de-energized or off. From now on, we should be saying off, not de-energized, because you don't energize a bit. You set it on or off. You set it in one state or the other. This instruction is true if the bit that it addresses in the PLC's memory is energized or on. Let's do this again. This instruction is true if the memory location addressed by this instruction, if the bit in memory addressed by this instruction is off. This instruction is true if the memory location, the bit in memory, the memory location addressed by this instruction is on. This instruction is false if the memory location, the bit in memory, if the memory location addressed by this instruction is on, because this instruction is really true if off. Now, Alan Bradley calls these two instructions XIC and XIO. I prefer to call this one true if off. Therefore, it's false if it's on. This instruction is false if the memory location, the bit in memory, addressed by this instruction is off. Okay, this is a normally open push button. And this is not part of PLC programming, but there is a certain situation when programming a PLC that you might run into which is confusing, and that is the difference between when you have a normally open contact or a normally closed contact wired up as an actual input device. Remember, a push button is an input device. So normally open push button is spring-loaded in this position, the open. When you press the button, a normally open push button, this is now held closed. So when you're pushing the button, you have continuity, and if this is wired to an input of a PLC, that input is on. This is a normally closed push button, and it has continuity when you're not touching it. So if this is wired up to a PLC input and no one's touching it, the input is on even though this button is not pushed because it is normally closed. Now don't forget this. So if we push the button, the contact is broken, the input that it's wired up to goes off. So a normally closed push button, when you push it, the input that it's wired up to will go off. So remember the difference between normally open and normally closed contacts out in the field. In the actual input field circuitry, they're just the opposite of each other. Okay, normally open push button, normally closed push button. Look at those closely. There are cases where you want to initiate a sequence when a button is released. We especially see limit switches that are held opened or closed against their normal state. In these cases, we refer to these switches in their normal state held closed. With push buttons, you don't normally hold them closed. However, with limit switches, it is possible the machine could rest against a normally open limit switch and hold it closed. Or with actual push buttons, you may have a situation where you have to hold the button down for a specific length of time. You have to exceed that interval, otherwise the logic in the PLC ignores it until after a timer has timed out, and the same would go for a normally closed push button held open. What this does is this prevents triggering logic by accidentally bumping these push buttons. Continuing on with our relay panel, remember that we still are representing the logical landscape with 8,192 rows of 16 relays. We're only showing the coils because the coils really represent the individual or collective state of all the conditions that we're working with in our logical program. So let's zoom in on just one row, row 1, coil 0 through 15. Now let me explain something. The layout or the actual location of a coil is defined by row and coil. Row 1, coil 0 through 15. But that's not necessarily the name of the coil. For instance, so far in our presentations, we've used the designation for a contact relay as 1CR. It means it's the first one that we assigned as we were creating our logic, and then the next one would be 2CR, 3CR. That doesn't mean that 1CR is the second relay coil from the right in any one of these rows. In other words, 0 through 15. So it's not 0CR, 1CR through 15CR. This is the physical location, not the logical location. Keep that in mind. Now we're going to take these 16 relay coils, because remember the coils represent the state. The state of the coil represents the state of the collective devices that control that coil. Okay, now we're looking at those same 16 coils, row 1, and coil 15 is the one that we have assigned the name to 1CR. These are all contact relay coils. We haven't changed to bits in memory yet. So if you look at our diagram here, this portrays a connection between an actual input device, the relay coil, and the relay contacts. Always remember that there is no electrical connection between the input device and the relay contacts that represent their state. So 1CR represents the state of that pressure switch in the field wiring that runs off of 24 volts DC. 1CR-1 and 1CR-2 also represent the state of that coil 1CR, which represents the state of the pressure switch. You could say that 1CR-1 and -2 also represent the state of that pressure switch, but only because that pressure switch is wired up field wiring wise to that coil. The actual input devices turn relay coils on and off, and the contacts read the state of those coils. You could say that the relay coil controlled by the input device represents the state of the input device. Looking at the input device, it is a pressure switch. When the pressure reaches a pressure that was set, it is said to have reached its set point. So that pressure switch has a dial on it that you can't see in the diagram, and you set that dial for a particular pressure, PSI. When that pressure is reached, that particular sensor is going to close. As you can see, it's normally open. It's held open by a spring. The spring tension is adjusted by that knob that controls the set point. At this point, the contacts in the device change state. The device can have both normally open and normally closed contacts. However, the pressure switch is not wired directly into the control panel's logic. The state of this input passes through a device that isolates the field voltage from the electrical circuits of the control panel. Looking at this diagram, with the state of the input as shown, and with what you know about the contacts that are identified as being controlled by this input device, are either of the contacts true at this moment? When I say either of the contacts, I mean 1CR-1 and 1CR-2. The pressure switch is open in the field wiring, which means that 1CR is de-energized. So are either of these two relay contacts, 1CR-1, 1CR-2, are either one of them true? Correct. The true if off, because the relay is off because the pressure switch is unconnected, it's not completing the circuit. The true if off contact that is identified with the relay coil is true because the coil is off. So the contact is true because the coil is off, and the coil is off because the field device, the pressure switch, is open. Remember, the contact reads the coil, not the pressure switch. Now you're saying in this case, isn't it one and the same? In some cases it will appear one and the same. In other cases it will not be, as you'll see later. What do you think will happen when the pressure device reaches the set point? Correct. The state of the contacts change, allowing free electrons to pass through the coil of the relay, energizing it. Consequently, the contact that was true is now false, and the contact that was false is now true. So 1CR-2 is now true because it represents 1CR, which represents the pressure switch. Remember, the relay coils are data that represent the state of the field devices, such as proximity switches, photoelectric switches, limit switches, conditional switches, etc. However, the contacts mechanically connected to these relay coils do not exist in the scheme of things unless you use them. That is, The contacts are wired into other circuits that control other relays or that control output devices such as motor starters, panel indicators, solenoid valves, etc., etc. This is why we separate the coils from the contacts logically in our diagram. Okay, let's run this diagram through a time machine. Watch closely the transformation from relay coil and contacts to a bit in the memory of a PLC and the basic instructions that address these bits. Watch the location of the coil change as well to a memory location. So what was coil 15 is now bit 15. What was row 1 is now word 1. Now there's an I in there, word I colon 1. The I is in there to signify that this 16-bit word in memory is part of the input, I for input, part of the input image table. So look this over closely. You still have your pressure switch. It's still 24 volts DC. Another inclusion here, if you will, the row of yellow relays in our original relay panel was the electrical interface between the field device voltages and the voltage on the panel. We have now replaced those special relays that interface the field voltage to the panel voltage with something called an optical isolator. So that little square you see there with a diode, a couple looks like bolts of lightning that just indicates light, and then a phototransistor, and it's part of the input module. So the input module specifically is the electrical interface between the field wiring and bits in memory. The memory is most likely powered by 5 volts DC, where the field wiring could be anything from 24 volts, 115 volts, etc. So this optical isolator, and if you look closely at it, you can see that there's an airspace, so to speak, between the field wiring and the output side of the optical isolator that is connected to bit 15 of word 1. This optical isolator is made up of 2 components. Now there's actually more components than this, but for the sake of illustration, representation, we have a diode. That's the black arrow with the point of it against a flat line. There's a cathode and an anode here. Now the direction of the arrow is in the direction of conventional current flow. Remember, we explained in an earlier lecture that early on in the days of scientific discovery that they named the 2 polarities positive and negative, positive meaning excess, negative meaning deficiency. And that's the direction they thought that current flowed. Well, it turns out that actually the component that moves, the electrons, flow from negative to positive, which means they would flow against the arrow. So regardless of whether you want to use electron flow or conventional current flow, this diode, this arrow, it's a rectifier. It only allows current to flow in one direction. This particular diode is an LED, light emitting diode. So when you apply voltage across this diode and you have current flow, which electron flow would be from the bottom against the arrow up to the top, it emits light. To the right of this optical isolator is a transistor. It's a 3-layer device, meaning that it has a emitter, a base, and a collector. The base, though, instead of having a wire or a conductor connected to it, is sensitive to light. So look at it this way. The 2 little bolts of lightning there, the light coming from the LED hits that flat line that's part of the phototransistor. That basically is sensitive to light. And you have a voltage applied from the bottom of that phototransistor to the top. We're talking about the right side of this opto isolator now. the flat line with the two lines that come in at an angle. One of them has an arrow on it. So you have a voltage applied across this from top to bottom. When light strikes the flat line, which is the base, it allows it to conduct. So basically you could say when you turn the LED, the light emitting diode, on the left, when it goes on, the transistor conducts electricity. When the light emitting diode on the left goes off, the phototransistor on the right shuts off. So we illustrate this. We have current flowing through the LED. It produces light, hits the base of the phototransistor, and you have current flow. So if the input is on, in other words, if that pressure switch closes, you have conduction, and then you have conduction through the phototransistor to the bit memory. When it goes off, you no longer have transmission to that bit memory. Okay, a little more detail. This is a diagram that portrays the connection between an actual input device and the PLC's memory. Always remember that there is no connection between the input device and the ladder logic instructions that use their state. The actual input devices turn bits in memory on and off, and the instructions read the states of those bits. Just like a contact on a relay basically reads the state of the coil. You could say that the bit in memory controlled by the input device represents the state of the input device. Looking at the input device, it's a pressure switch. When the pressure switch reaches a pressure that was set, it has reached the set point. At this point, the contacts in the device change state. The device can have both normally open and normally closed contacts. However, the pressure switch is not wired directly into the PLC's memory. The state of this input passed through a device that isolates the field voltage from the electronics of the PLC. This is called an optoisolator. And the optoisolators are normally packaged in groups of 16, placed into a separate module that is slid in and out of a rack. So if you have a particular type of device you want to integrate into your PLC, you buy an input module that has the correct optoisolators to integrate that input device into the PLC. When the input device completes the field circuit, the free electrons flow through an LED that illuminates a photoreceiver, allowing current to flow to the bit memory. The sole purpose of this device is to isolate the field voltage from the PLC circuit. This arrangement allows all manner of input devices to connect to the PLC without needing a relay to isolate it. Remember, in our earlier presentation, we used the isolation between the coil of a relay and its contacts to isolate the field voltage from the logical voltage on the panel. The reason that it is important for you to understand this is because a big part of the market and a major component of all PL systems are the I/O modules. These are the individual modules that allow different types of field devices to interface into the PLC's memory. Looking at this diagram with the state of the input as shown, and with what you know about the instructions that are addressing the bit in memory controlled by this device, are either of the instructions true? Correct. The true if off instruction that is addressing memory location I for input, row 1, coil 15 or bit 15 is true because the bit in memory that it is addressing is off. So the instruction is true because the bit is off in memory, and the bit in memory is off because the field device, the pressure switch, is off. Remember, the instruction reads the bit in memory, not the pressure switch. What do you think will happen when the pressure device reaches the set point? Correct. When it reaches the set point, the pressure switch closes. Now I don't show it, I'm not animating it to show it close. Instead, I just highlighted it in green to show that the circuit is complete in the field wiring. The state of the contacts changed in the pressure switch, allowing free electrons to pass through the LED in the optoisolator, thereby turning on the associated bit memory. So you see bit 15 now of word 1 now shows that it's on with a green circle. Consequently, the instruction that was true, which looks like a normally closed contact there, it was true before we turned this on. It's now false, and the instruction that was false is now true. While the PLC is in the run mode, the logic is continuously reading the bits in memory that they are addressed to and updating the logic. Well, we've made a few changes here. Let's fatten up our diagram with more than one input and change the device to momentary contact push buttons. We did have a normally open pressure switch in there. Now we have a normally closed and a normally open push button. There are two push buttons in this diagram. What is the difference between the two? Correct. The first one has a normally open contact. The one on the top has a normally open contact, and the second push button has a normally closed, which means when neither button is touched, being pressed, depressed, the top one, a spring holds it open, and the second one, a spring holds it closed. Normally open, normally closed. Okay, consider their normal state as you see them right now. Are either of the two input devices completing their input circuits to the PLC? So the question is, are either one of these two supplying voltage to the input module to turn the bits on in memory? Give you a second to think about that. Correct. The normally closed push button connected to bit 14 of word 1 is a completed circuit, and the free electrons are flowing through the optical isolator and turning on bit 14 of word 1 in the PLC's memory. Look closely at the PLC instructions that look like relay contacts. Remember, we're making the transition from relays to bits in memory. So we substituted actual electronic bits in memory for the relay coils, and for the contacts we're substituting logical instructions. And they look like normally open, normally closed contacts, but they're not. They are instructions that are true if on, true if off, based on addressing a bit in memory. And you can see each instruction has right above it input colon 01/ and a bit number. That's analogous to a coil number of row 1. Okay, look closely at the PLC instructions that look like relay contacts. Compare their state to the bits of memory that they are addressing. Which instructions would be true with neither push button actuated? In other words, right now no one's pushing any buttons. Which of these instructions would be true? Correct. True if on instruction addressing bit 14 is true because that circuit is complete, turning on that bit in memory. But the true if off instruction addressing bit 15 is true because the circuit for input 15 is not on and the bit in memory is off. So here's a major point of confusion for many people making the transition between relays and PLCs, even though it makes perfect logical sense. The problem is this is a normally closed push button, so when it's not pressed, the bit is on in memory and the true if on instruction is true. So a lot of people look at this and say, well, if you're not pushing the push button, then how come that instruction that looks like a normally open addressing bit 14, how come it's true if you're not pushing the button. It's true because the circuit is on in the field wiring. Has nothing to do with whether the push button is pressed or not. When you write code, when you read code, you have to know what kind of contacts you have in your input devices, because not just push buttons have normally open, normally closed. All the other sensors have the ability to connect up a normally closed or a normally open contact to the input. You can set photo eyes to what they call light operate and dark operate. Two different modes of operation. One of them turns on the bit memory if it doesn't see anything, and the other mode of operation turns it on if it does see something. You have to know what you have in your input field wiring to relate that to the logic in your memory, those instructions that look like normally open, normally closed. So the only real way to look at these instructions, when you see that instruction that's true right now, I:01/14, that looks like a normally open contact. It's true because bit 14 is on. You want to isolate that in your mind from what it's actually hooked to out there in the field, unless you're writing the code. If you're writing the code and you want to know if that button is closed, which it is right now, the one hooked to bit 14, it's closed. If you want to know if no one's pushing it, then you need to use the true if on instruction because the bit is on, bit 14 is on. Let's elevate word input :1 to the top of the diagram to emphasize it. This makes it a little bit easier to look at. So rather than work in the small definition down there in process memory, we'll elevate this word and continue. Before we depress the push button, run through this action in your imagination and visualize what you think will happen. Okay, we have a finger poised above the normally closed push button. What is going to happen in the opto-isolators and in memory, and how will the instructions change their true-false status when you push that button? When the normally closed push button is pressed down, it forces the contacts open. The input circuit is now incomplete, and bit 14 of word input :1, input word 1, in the PLC's memory is now off, and the instructions that address it must change from true to false and false to true. So you see, when we push that button, the only thing that changed in the logic is the two instructions, both addressing input :01/14. The one that was true went false, and the one that was false went true. So look at the state right now. Of the two instructions addressing bit 14, which one's true, which one's false? That's right, the top one's true because it is true if the bit that it is addressing in memory is off. Why is that bit 14 off? It's off because you opened up the field wiring. Whether you did that by letting go of a normally open button or pressing a normally closed button, that only matters when you're actually writing your code to decide which of the two instructions you want to use. But get this straight in your head. When you press a normally closed push button, the bit memory goes off and the true if off instruction becomes true. Because when you push the button, a normally closed button, you're basically, when you push it, you're breaking the circuit and it's now off. So the true if off instruction is true. You want to look at it that way. Let's try another push button. What would you expect this to do when you press this button? Now remember, we let go of the normally closed push button. It's now conducting again, and bit 14 is back on, correct? So the input device connected to bit 14 is closed, completing the circuit that turns bit 14, that turns on bit 14, and the instructions true if on and true if off reflect the state of bit 14 in memory, which reflects the state of the input device, correct? The input device connected to bit 15 is open, and the circuit that turns bit 15 on and off is keeping bit 15 off, and the instruction addressing bit 15 reflects this state. Correct? If you look at the two instructions that address bit 15, true if on is false right now, that's on top, and then right below it, true if off is true because bit 15 is off. So if we push the button, the push button's contacts close, completing the circuit, allowing free electrons to pass through the LED in the optoisolator, casting light on the phototransistor, which conducts, turning on bit 15 in the PLC's memory. And the instructions that address bit 15 of word input 1 reflect the state of bit 15, which reflects the state of the normally open push button now being depressed. Not depressed, depressed. You see, the only thing that's changing state is bit 15, so the instructions that query bit 15 are changing state. Normally open, not pressed, true if off instruction is true. The true if off, it looks like a normally closed relay contact addressed by input :01/15. You're not pushing the button and it's true. You push the button, it goes false and the other one goes true. Okay, if you look up above, you see both bits in memory are on. Bit 14 and bit 15 are both on. One button is being pushed and the other is not. Make sure that you continually reflect on this when you're writing your code and you're analyzing logic. Just because the bit in memory is on doesn't mean that someone pushed the button, because it might be normally closed. That's why typically we use nothing but normally open contacts in our input devices, because that's what people expect. They expect if there's nothing there, nothing being sensed, the button's not pushed, they expect it to be off and the bit in memory to be off. So we can use normally closed push buttons because normally closed push buttons fail safe. For instance, let's say that normally closed push button was a circuit stop or a motor stop, and if the wire became broken or the switch became defective and the circuit opened, then that declares that the button has been pushed even though it really hasn't. So if it's a button that when you push it requests a safe state, then you want to use a normally closed push button, because if it opens, wire breaks, forklift backs into the machine, breaks the conductor, operator gets mad, bangs on the switch and breaks it, it fails, but it fails to the safe condition. So that is typically the conventional use of normally closed contacts, is if you want a fail-safe condition. Well, we've really enhanced our graphic now. We've expanded it not only to include a rung of relay ladder logic, not a relay circuit. This is not a normally closed contact, normally open contact, but this is a true if off instruction, true if on, and an energize output. And we still have our two inputs, they're push buttons. However, this one is now a normally open. So both of these push buttons are normally open. We also have an output, a solenoid. So this could be a solenoid that operates a cylinder. Notice also we've expanded our memory from 1/16-bit word to more than a half a dozen. And because I looks like 1 and output O looks like 0, we're putting our output image on the bottom and then our input image next up to that. So here's our output image. We have 4 words of output image and 3 words of input image. So now we have more bits in memory to work with. Let me ask you a question. If word I1, that means word 1 of the input image, and bit 14 if it represented a de-energized relay coil instead of a bit in memory, would this contact be open or closed? And I call it a contact because we're relating it to a coil of a relay, not a bit in memory. So if this normally closed contact were associated with a de-energized relay coil, would this contact be open or closed? If the relay is de-energized and that's normally closed, then it would be closed. Why would it be closed? This contact is normally closed and the normal state of a relay coil is de-energized. So once again now we're kind of jumping back and forth between the relay symbols and the ladder logic symbols relating coils of relays to bits in memory. If input word 1, bit 15 represented a de-energized relay coil, would this contact be open or closed? De-energized. That's right, it would be open. Why would it be open? This contact is normally open and the normal state of a relay coil is de-energized. With neither push button pressed, are any of the inputs on? No. With none of the inputs in memory on, look at your field wiring for your inputs. Neither switch is pressed, so you have no complete circuits, no current flowing through those LEDs to light up the bases of the phototransistors, so neither one of those bits in memory, bit 14 or bit 15, are on. With none of the inputs on in memory, are any of the instructions in this rung of logic true? Think very carefully. Remember, both bits are off. Look at the instructions up there. Are any of them true? Yes. Input word 1, bit 14 is true because that's a true if off. Bit 14 is off, therefore it's true. So you have something that looks like a normally closed relay contact that's true when the push button is open. This is where you can get confused when you try to match up the symbols with the field wiring. That instruction that is highlighted right now is true because it is reading bit 14 of word 1 in the input image, and it is true if off, and bit 14 is off because the button is not pushed. If we pressed this push button, what is the effect in memory? So we're going to push the button connected to bit 14 in input word 1. What will be the effect in memory? That's right, it'll turn on bit 14. With this input in memory on, are any of the instructions in this rung of logic true? Remember, we have true if off, true if on. So we're talking about bit 15 is off, bit 14 is on. Are there any of the three instructions, and I'm talking about these right here, true if off, true if on, true if on. Only one of them addresses bit 14. Is this true if this bit is on? No. That's a true if off instruction. Why? Because it's a true if off instruction. Would you say or state this rung of logic? How would you say or state this rung of logic? In other words, if you wanted to put this into a sentence, how would you say it? Well, let's try it the long way, and then maybe we'll try it a couple shorter ways. If off and if on, or if on then let. That is the terminology that's normally used in programming language. If it's off or if it's on, then let such and such. Is there any connection between any of the instructions in this rung of logic and any of the input circuits or output circuits? Absolutely none. That's because the logic is totally independent of the functionality of controlling the input bits and transferring the output bits to the output devices. What's going on in ladder logic is solely within the memory. It has nothing to do with the field devices. Now the field devices, especially inputs, affect the state of memory bits, but the ladder logic itself only operates with the state of memory bits. The logic independently reads and writes to memory. You create the hardware image and then you write the logic based upon your knowledge of these assignments. The connection exists solely in the mind of the observer. The input and output devices cannot see the logic, nor the logic see the input or output devices. So if I was going to state this rung logic, I would say if bit 14 is off and bit 15 is on, then turn on bit 0 of word 2. Or if bit 14 is off and bit 0 of word 2 is on, then turn on bit 0 of word 2. Now you're probably wondering, how could it be on if no one turned it on? That's a good question. We'll get to that. So if bit 14 is off and bit 15 is on, or if bit 0 is on, then let bit 0 be on. Now this only works if bit 0 in the output word 2 is already on. So basically, if bit 14 is off, look at bit 14 and 15 there in blue. If bit 14 is off and bit 15 is on, then that rung of logic is true. It then, with the output instruction, the OT, output energize, sets bit 0 of word 2 in the output image to on. The next time you come through and read this rung of logic, now the true if on instruction right below bit 15 instruction, it's now true. So if you were to lose bit 15, in other words, if it were to go off, bit 0 of word 2 is still on. So you still have a true path over to the output instruction that turns on bit 0 of word 2. Is there any connection between the instructions in this rung of logic and the input and output devices? Absolutely none. Why? Because the instructions read the bits in memory. They don't read the input devices. By the way, notice that this instruction right here is actually reading this bit over here. So your instructions, your conditions or permissives are not limited just to input words. They can read output words as well. Are any of the input or output devices on? Right now? None. Are any bits in memory on? Nope. Are any of the instructions in this rung of logic true? Remember, both the input devices are off. Now think carefully before you answer. Are any of the instructions in this rung of logic true? Of course. Bit 14 is off, therefore that true if off instruction is true. Bit 14 is off, therefore true if off is true. What happens if we push the push button connected to bit 14? That would be the bottom one over here, the normally open push button. What happens if we push the push button connected to bit 14? It turns on bit 14, and now the instruction that was true is now false. So someone's pushing the button and the bit is on, but the instruction is false. Are any of the input or output devices on? Yes. The input device connected to bit 14 is on. Are any of the bits in memory on? This is not a trick question. You can see the answer right there on the screen. Of course, bit 14 is on. Are any of the instructions in this rung of logic true? That's with bit 15 off, bit 14 on, and output word 2 bit 0 is off. No one ever turned it on. Are any of the bits in memory on? Of course, bit 14. Why? Because the push button that's connected to the opto isolator that controls bit 14 is pushed right now. It's on. That's why it's highlighted. Okay, both push buttons are released. The true if off instruction is true. What happens if we push the push button connected to bit 15? That bit is in memory is switched to the on state. So if we press that button, then that bit in memory goes on. Does this instruction become true immediately when the bit goes on? No, it doesn't. Why doesn't it? Not until the program scan reaches this rung of logic for the first time after the bit in memory is switched on. Now, everything happens so fast it seems instantaneous, but there's really a sequence of events over a period of milliseconds, thousandths of a second. And in programmable logic controllers, a thousandth of a second is a long time. So, when the push button was pushed, the bit went on, but the bit memory is not on for a few, maybe milliseconds. The bit goes on in memory, but the program scan, until it reaches that rung of logic, reads that instruction, which reads that bit memory. That instruction is not true. Once it becomes true, what happens after this instruction is true? The processor reads memory location, output word to bit 0 to determine if this instruction is true or false. The entire rung of logic is analyzed, then the OTE is executed with this true execution. So the rung is true already, but it always reads from left to right, top to bottom, and then executes the output instruction. So the OTE is not going to be executed until the whole rung of logic is executed. When that happens, this true state of this rung, because those two instructions for bit 14 and 15 are true, then output word to bit 0, it's not true. It is turned on by that output instruction, that OT instruction. Now, does the output solenoid energize immediately? No. Output word to bit 0 is turned on immediately, but it's not transferred out to the solenoid valve until the program is done scanning and the output image is executed. Does this instruction become true immediately? Now remember, this instruction was false on the last scan because output word to bit 0 was not on yet. Now it's on. So the next scan around, it comes down. And by the way, you're still holding that button down, because this all happens in a couple milliseconds. I don't care how quick you are. If you're Flash or Lightning Johnny, you can't push that button and release it in less than a couple thousandths of a second. Which means if you push that button with your finger, it's going to stay pushed for at least 5 to 10 program scans. On the first scan, bit 15 was on, so that instruction was true, so it turned on that bit in the output image. Output image word to bit 0. The next scan through, it reads bit 14, it's off, so that's true. It reads bit 15, that's on, so that's true. It reads bit 0 of word 2, that's now on, so it's going to declare it as true. Then it turns on bit 0 of word 2 the output image. But you say, wait a minute, it's already on. That doesn't matter. The PLC is not that smart. It doesn't know the bit's already on. It just turns it on every single program scan. So every single program scan that this rung is true, it turns on that bit in memory. Now it was already on, so it's redundant. But remember, this instruction, the OTE, output energize, that's setting or resetting bit 0 of word 2 the output image. It has a true execution and an off execution. Every program scan that the rung is true, it's telling that bit in memory, bit 0 of word 2, you're on, you're on, you're on. Stand up, you're on, stand up, stand up. Now when the rung goes false, then every single program scan, it's going to say, hey, bit 0 and word 2 of the output image, you're off, you're off. Sit down, sit down, sit down. You're off, sit down, sit down. You see what I'm saying? It has a true and a false execution. So when the rung's true, it executes the same function every single scan that the program is true. When it's false, the rung is false, it has the same false execution and it executes it every single program scan. Why is the instruction addressing input word 1 bit 15 still true? Well, you're still holding your finger on the button. That bit in memory 15 is still in the on state. That's why it's still true. You haven't let go of the button yet. What happens if we release the push button connected to input word 1 bit 15? Bit 15 goes off, that instruction goes false, but look, the next program scan, it sees the bit 14 is off, so it's true, but it reads word 2 of the output image, bit 0, before it executes the OTE. It reads it, it sees that it's on, so it turns it on. This is called a seal-in or self-sustaining logic, seal-in logic. Very important thing to understand about relay ladder logic is this functionality. Now this works the same with relay contact. So that instruction that looks like a normally open contact, which addresses bit 0 of word 2 of the output image, that would be a contact that was part of that relay coil over there, which is an OT instruction. You see they're addressing the same bit, right? Therefore, that contact would be part of that coil. So if that coil is energized, it's holding that contact closed, bypassing the push button hook to bit 15. Why is bit 0 of word 2, the output image, still in the on state? We just answered that. None of the inputs are on, right? Look over there, bit 14 and 15 is off. But the true if off instruction that addresses bit 14, it's still true because 14 is off. 15 is off, so the instruction that addresses bit 15 is false, but we have the instruction addressing bit 0 of word 2, it's still on, so it's still true, so it holds itself on. If bit 14 is off, so that the first instruction is true, the logic reads bit 15 and it is off, so the second instruction is false. The logic reads bit 0 of word 2 and it is on, so that instruction is true. The rung is true and it executes the true execution of the OTE, turning on output word 2 bit 0. The fact that it is already on is irrelevant. The logic energizes at every scan that the rung is true. The same is true when the rung is false. No buttons are being pushed right now, and bit 0 of output image word 2 is on. And every single program scan, as long as this rung is true, the true execution of that instruction, that OTE instruction, will set that bit to 1. It'll turn it on. Now, the fact that it's already on is irrelevant. The rung only knows whether it's true or false. If it's true, it turns the bit on. If it's false, it turns the bit off. If it's already off, then it tells it to turn off, the result is still the same. So how do we turn this, how do we make this rung go false? Well, what happens if we push the push button attached to bit 14, which is normally open? Now, if you look at your logic right now, the first instruction, true if off bit 14. Well, 14 is off, so it's true. So if we press the button, 14 goes on, that rung goes false, and it turns off bit 0 of the output image word 2. The next scan, that instruction is also false. And when we let go of that button, then the instruction, the true if off instruction, will go back true again. But neither bit 15 is on nor bit 0, so the rung still stays false until you push the top push button that turns on bit 15 again. Okay, how would you do this with a normally closed push button? Remember, we like normally closed push buttons. We like normally closed contacts in any situation where we want to fail safe or fail off state, meaning the field device fails, either the wire opens or the device breaks. So with a normally closed push button for a stop button, you have continuity all the time. Bit 14 is on, as you can see, no buttons pushed. If the button were to break, then that input would go off, and so would bit 14. So it would be fail-safe. So we also have to change the instruction that reads the bit from a true if off to a true if on. Now remember, whenever you want a rung of logic that has one event that makes the rung go true and stay true, and another event that makes the rung go false and stay false, you need the right combination of field devices and logic. So in our previous example, I'll just back up to that. You see we have a true if off instruction reading bit 14, and we have a normally open button, and that worked for us. Moving forward, now we have a normally closed push button, so we need a true if on instruction. In other words, no buttons being pressed right now, so the first instruction is true. When we press the start button, then that input turns on bit 15, so the second instruction is true. It turns on output word to bit 0, which turns on the solenoid. Next scan through, it reads that, remember this is a read instruction now. The previous scan we wrote to bit 0. This one we're reading from bit 0. So we see that that is on. And when we let go of the push button that started this whole thing, we have a rung that's being held on. Now how would we shut this rung down? How would we make this rung go false? Well, we would press the normally close button, bit 14 goes off, that instruction goes false, turns off bit 0, turns off the solenoid. This concludes this presentation. Thank you for watching. I hope you both had a good learning experience and that you enjoyed yourself. Again, thank you. Once again, thank you for watching the PLC Professor's training videos. This particular lecture can be used as a standalone lecture. I try to make it as generic as possible. The examples that I used were on occasion specific to the Allen Bradley Micrologics family. Also on the PLC Professor YouTube channel you can find a lengthy video on how to use free software to create a simulator. You can go to www.plcprofessor.com and purchase the electronic PDFs for the training manuals, the lab project manuals that go along with the majority of the videos, or I should say the majority of the videos on this channel are discussions and lectures relating to the lab projects in those three manuals available on the plcprofessor.com website. You can also order the printed forms of the manuals. They're considerably more expensive than electronic because color printing is very expensive. I am going to edit the three manuals back into one manual and see what it costs to print it as one manual. Again, thank you for watching. If you do purchase the electronic PDFs, we appreciate that you do not share these with other people. We priced the electronic versions inexpensive enough that everyone can afford to buy their own, and the revenue from these manuals is the only revenue that supports creating more of these videos for the PLC Professor YouTube channel. Once again, thank you.